This is Swathi, working as Assistant Professor in the Department of Electronics and Communication Engineering in Institute of Aeronautical Engineering, Dundigal. Welcome to this lecture. In this lecture, we'll discuss the tutorial question bank on Module 3, that is number systems, and also minimization of Boolean functions using K-map. So here, we already know the basic concepts of number systems. What are the various types of number systems we have, how to convert the number system, a number from one number system to the other number system, we have seen. And also we have discussed so many binary codes like weighted codes, non-weighted codes, error detection and correction codes we have seen. And we have also seen the Boolean algebra, and that how to simplify the Boolean functions using Boolean algebra, and the basic logic gates we have seen. So these are all the topics that were covered in Module 3. So we will be discussing how the questions are asked on the number systems, that is also on the binary codes like weighted, non-weighted codes, error detection and correction codes. What do you mean by complement? How the complements are used in subtraction of two numbers, like that. There are so many questions that may be asked on this number systems. So first let us start with problem solving and critical thinking questions, that is part A. So the part A consists of 10 problem solving and critical thinking questions. So first we'll start with that part A. So convert the following hexadecimal number to their decimal equivalent. So an hexadecimal number is given, which is EAF1 16 to the base 16, and now we need to convert this into its equivalent decimal number. So how to convert this into equivalent decimal number? So we know that each and every digit in any number of any base will have its own positional weights. So using that positional weighing method, so we are going to convert a number from any base, not only hexadecimal, we can also convert any base into decimal by using that positional weights. So here, as you all know that the positional weights of a hexadecimal number system is expressed in terms of, or else it's expressed as powers of 16. So this is the position 0, 1, 2, 3. It is a 4-bit hexadecimal number, 4-digit hexadecimal number given. So the positions are given like this, 0, 1, 2, 3. So where the positional weight of this one is 16 power 0, 16 power 1, 16 power 2 and 16 power 3. So multiply each digit with its positional weight and add all the products together so that you will be getting the equivalent decimal number for the given hexadecimal number. So that is E. What is the decimal equivalent of E? So E in decimal can be represented as 14. 14 into 16 to the power of 3 plus A in decimal is represented as 10. 10 into 16 to the power of 2 plus F is 15. 15 into 16 to the power of 1 plus 1 into 16 to the power of 0. So add, these are all the products, nothing but each digit multiplied by their own positional weight, and add all the products together so that you will be getting its equivalent decimal number. So this is the problem. This is the solution. Like that you have to write. So first you have to write down the procedure how to convert a given hexadecimal number into decimal number. For that you will get some marks, and then you have to do the problem. If the steps are correct, then also you'll get this marks, and if the answer is also perfect, then you will be getting full marks. So this is how, not only writing solving, if you write the procedure to convert hexadecimal into decimal number, it will be well and good. Now, what is the second question? What is the gray code equivalent of the hexadecimal number 3A7 and find its 9th complement? And not its ninth complement, just gray code equivalent of hexadecimal number. Find the 9th complement of 25.639 to the base 10. So here he has given hexadecimal number and he asked us to find out the gray code for this one. So in order to find out the gray code, first we need to convert the given hexadecimal number into binary. So how to convert a given hexadecimal number into binary? Replace each digit of hexadecimal number with its 4-bit binary equivalent. So what is the number given? 3A7. So this is hexadecimal number. Now I am going to convert it into binary. So 3 in 4-bit binary can be represented as 0011. And A, what is A? 10. 10 in 4-bit binary number, 10 as a 4-bit binary number is 1010. Whereas 7 is 0111. This is the binary equivalent. So once the binary code is available, then we can easily convert this one into a gray code. So simply by following the procedure of converting a given binary number into gray code. How to get the gray binary, convert the gray code into, binary into gray code? MSB is considered as same. So the XOR of the consecutive digits will be giving the next digit of, or else next bit of gray code. So 0 XOR 0, 0, 0 XOR 1, 1, 1 XOR 1, 0, next 1 XOR 1, 0, 1 XOR 0, 1, 0 XOR 1, 1, 1 XOR 0, 1, and then 0 XOR 0, 0, 0 XOR 1, 1, 1 XOR 1, 0, 1 XOR 1, 0. So this is the gray code equivalent for the given hexadecimal number 3A7. So the thing is, first we need to convert the given hexadecimal number into binary and then convert the obtained binary number into gray code by using XOR operation. Okay, so this is the first one. Next, find the nines complement. How can we get the nines complement of a given decimal number? Simply subtracting each digit of the given decimal number from 9, you will be getting nines complement. So what is the number given? 25.639. So now I want to get the nines complement. So subtract each digit of the given decimal number from 9 so that you will be getting the nines complement. So 9 minus 9 0, 9 minus 3 6, 9 minus 6 3, 9 minus 5 it is 4, 9 minus 2 it is 7. So that is the nines complement of 25.639 is given by 74.360. So like that you can get the nines complement. So first, whatever you are doing, write down some steps of getting the nines complement. So what I said, the nines complement of a decimal number can be obtained by subtracting each digit of the decimal number from 9. We can get the nines complement. Just write down this in words and then do that procedure so that find out the answer here. This is the way. And then implement a 7-bit Hamming code for the given message 1010 by using odd parity. How to convert, how to generate the Hamming code? So for that, I'm taking an empty slide here. So what is the message given? So the message given here is 1010. So we already know the procedure of generating Hamming code. What is that? First, we need to find out the number of parity bits to be added, right? So how can we find out the number of parity bits to be added? So we have to satisfy the condition n 2 power k must be greater than or equal to n plus k plus 1, where k is the number of parity bits to be added, n is the number of message bit or else number of bits in the message, or such that we need to select the k value such that this condition is satisfied. So for this, if I choose k is equals to 2, trial and error method, k is equals to 2, it will be 4. And what is the number of bits in the message given? 4 plus 2 plus 1. Is 4 greater than 7? No. So the condition is not satisfied. Now we have to choose k is equals to 3. So if I choose k is equals to 3, it is 8. So this is 4 plus 3 plus 1. So it is equal to 8 equal to RHS and LHS are equal. So the condition is satisfied. So now our Hamming code length. So already we have discussed this in some other lecture. So if you have any doubt, you can just go through that. So Hamming code length will be n plus k, that is 4 plus 3, 7. So we need to construct a table. So which is stating like this: bit designation. Next, binary position. Sorry, first is bit position. First is bit position, and then bit designation, and then binary position, and then message bits, and then parity bits. So this is how we can construct a table. So for that, so how many bits are there in the resulting Hamming code? 7 bits. So the bit positions can be given by 7, 6, 5, 4, 3, 2, 1. Like this we have to give that, right? So then what should we do? Bit designation. So we have to remember that all the parity bits should be placed in the powers of 2 position. 1 can be represented as a power of 2. So I can give it as a parity 1. Even 2 can also be represented as a power of 2. So even this can be used for a parity bit. And 4 can be used as, again, represented as a power of 2. So the 4 can be used for the parity bit. And the remaining all are the message bits. M1, M2, M3, M4. Right? Now, binary positions. So we have given positions for the Hamming code, right? So now we have to write down the binary equivalent for this position. So as we have 7 bits, so we require 3 bits to represent them in binary. So I'm writing the 3-bit binary equivalent for all these positions. 1 can be represented in binary as 001, 010, 011, 100, 101, 110, 111. Now the message bits. So you write down all the message bits according to the message given. So this is M3 and this is M4 and this is M1. So M4 is 1, M3 is 0, M2 is also 1, whereas M1 is 0. And we don't know the values of parity bits. So for finding out the parity bits, we need to check the binary positions or else bit positions whose binary equivalent is having its LSB as 1. So what are the binary positions which have LSB as 1? 1, 3, 5, 7. So anyhow 1 is for parity, just leave it. 3, 5, 7. So what are the values that are present in third position is 0. Next fifth is 1 and seventh is 1. So here we have to consider, if any parity is given, we have to consider that parity. If no parity is mentioned in the problem, we have to consider the even parity. So now we need to check whether the number of ones are even or not. So here it is even. So as we have considered the even parity, so as a number of ones in this particular group is even, so we have to consider the parity bit P1 as 0. If it is odd, then we need to take the parity bit as 1. So similarly P2, for finding out P2, we need to check all the positions whose binary equivalent is having its second bit as 1. So that is 3, 6, 7. 3, 6, 7. So what is the value in 3? It is 0. 6 is 0. Okay. And 7 is 1. So what are the number of ones here? 1. So which is odd. But what parity I should have? Even parity. So that is why I am taking parity bit 2 as 1. And similarly P3. So for checking P3, for generating P3, I have to consider all the positions which are having its MSB as 1. So those are 5, 6, 7. 5, 6, 7 is 101. So that means even number of ones we have. So P3 is also 0. So just write down the parity values which we have got here. P1 is 0, P2 is 1, whereas P3 is 0. Now the Hamming code. So include all the Hamming codes and along with the message bit. So that will be our 7-bit Hamming code which is to be generated before transmission. That is 101. The parity bit 3 is 0 here again and 0. And the parity bit 2 is 1. And this is our Hamming code of length 7 bits. So like that you can generate the Hamming code for any number of bits message it is given. So this is the procedure that we have to follow. First we need to choose the number of parity bits required to be added and then construct the table and first identify the length of the Hamming code, resulting Hamming code, and construct the table and find out the parity bit according to the algorithm defined by the Hamming. Okay, so this is how we can do that. So now coming to the fourth one, perform the subtraction of subtraction using 1's complement and 2's complement. So the problems given here are this is one problem. 2 problems are given in order to find out the subtraction or else in order to perform the subtraction of 2 binary numbers. So using 1's complement and 2's complement. So now let us try to do for 1's complement and then 2's complement. So you all must be aware of the procedure of performing the subtraction using complements. So we have some rules. What are the rules of subtraction? So first, I am discussing about ones complement subtraction. Ones complement subtraction. So ones complement subtraction, what we need to do? We need to consider the A is given as 11010, 11010, and B is what? B is given as 140s, 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 right? So what we are doing, we are performing the subtraction of 11010 minus 1000. So what we need to do, we need to get the complement of ones complement of negative number. What is the ones complement of this number? 0, changing ones to zeros and zeros to ones. 0, 1, 1, 1, right? After getting the ones complement, just add it to the A. So that is 1, 1, 0, 1, 0. Now perform the addition. So 1 plus 1 is 0 with a carry 1, 0 with a carry 1, 0 with a carry 1, 0 with a carry 1. So while you are performing the subtraction using R minus 1's complement, so the carry, if carry is generated, it is called as end around carry and it should be added to the LSB of the result. So that now I am adding here. So that is 1 plus 1 again 0 with a carry 1, 1, 0, 0, 0. So this is the subtraction result. So if you have any doubt, you can cross check it. What is the decimal equivalent of this one? This is 10 plus 10 plus 16, 26 minus minus 16. How? Just a second. Okay, if you perform the subtraction here, what I'll get? This is 0, 1, 2, 3, 4, 2 power 4, 16, 8, 24 plus 2, 26, and this one is 16, and we have to get the answer as, sorry, it is 1. Actually, it is 1. 1 plus 1, 0 with a carry 1, and again 0 plus 1 is 1. So we have 1 here. So now what is the answer we are getting? It is 10. So even if you look at the decimal equivalent of this one, this is 26 and this is 16. 26 minus 16 is 10. Finally, you are getting the answer as 10. So like that you can perform it. And even you can perform it using 2's complement. How can you perform this using 2's complement? Just get the 2's complement of a negative number. How to get the 2's complement? 1's complement plus 1 will give you the 2's complement. If it is then add the 2's complement of negative number to the positive number so that you will get the result. So in case of 2's complement subtraction, we need to follow that rules. What are that? If carry is generated, it is called as it is to be discarded. So if carry is generated in R's complement subtraction, discard the carry. If no carry is generated, then the result is negative, and we should get the R's complement, that is 2's complement of the result, and put a negative sign before. So like that you can perform the subtraction using 1's complement and 2's complement. I hope it is clear. If you have any doubts, you can just go through the video lecture that has been uploaded. So which is on the problems on complements, or else you can also go for the complement subtraction. Okay, so you can find the solution for this. Next, convert the following hexadecimal number into decimal. So just now I have I have told you how to convert a given hexadecimal number into decimal. Use the same procedure. What is that? Using the positional weight method. Positional weight method means multiply each digit of hexadecimal number by its positional weight, which is in terms of 16 powers of 16, and then add all the products. So the same thing we have to do for this. So this is the fifth problem. Now implement Boolean function A/B complement plus A complement B using 2 input NAND gates. So we have a procedure for implementing for realizing a Boolean expression using NAND or NOR logic. So use that procedure and implement a 2 input NAND gate using this logic function using to input NAND gates. What is that procedure? First, we need to draw the AOI logic for the given Boolean function. What is the given Boolean function? AB complement plus A complement B. Then second step. What is the second step? I want to go for NAND gate. I want to implement this one using NAND gate. So in that case, put or else place a bubble at the output of each AND gate at output of AND gate, and if even the circuit may include OR gates also, right? And at inputs of each OR gate. So we need to place the bubbles at the outputs of each AND gate and at the inputs of each OR gate, and then replace or else place a bubble. Third one is place bubbles. Place inverters on the lines on each line which has received a bubble, and eliminate double inversion. And finally, what we need to do, we need to replace the bubbled OR gate. That means we have placed bubbles at the inputs of OR gates, right? So all the bubbled OR gates should be replaced with NAND gates. So that is how we can implement the Boolean function. Not only this Boolean function, any Boolean function can be implemented using NAND gates using this procedure. Now simplify using the postulates and theorems of Boolean algebra. So we have so many theorems and postulates in Boolean algebra. So apply them and then simplify these Boolean functions. So for this we need to be aware of, or else we need to be familiar with the various theorems and postulates in Boolean algebra. Okay, so you can find the solution for this one on the in the video which has been uploaded on the problems on Boolean or minimization of Boolean function using K-maps. Okay, so you not K-maps, using Boolean algebra. So simply you can find it like this. So first of all, I'm taking the first problem. X plus y complement plus xy into x plus y complement into x complement y. So we have to expand this one. So that is, let us consider this as A into A plus B. So A into A plus B. Okay, A into A plus B. Right? A into A plus B. So what I can do this one? I can do this one as A into AA plus AB. So which is nothing but okay. Or else simply expand this one. So that means simply multiply this one, x into x plus xy complement plus xy complement. Okay, x into x plus xy complement plus y complement plus xy into x plus xy into y complement, and then x complement y, right? So x plus this one, it becomes 0. Okay, and this one also becomes 0. These two terms become 0. So x into x becomes x. So we are applying the rules here. Y into y complement as 0 and x into x as x, right? Next, xy complement. So this is also repeated. That is why I can write, so x plus x is equals to x, right? So I can write xy complement plus xy. Okay, so this is the equation we have got, and this is x complement y. So now I can write this one. I can take x as common here. I can take x as common in these three terms. So what I can get, 1 plus y complement plus y into x complement y. So that is 1 plus y complement y is 1, because 1 plus x, anything 1 plus x is equals to 1, right? So x into 1, sorry, not this. So x into 1 into x complement into y. So again we know that x complement is 0. So this becomes, entire function output becomes 0. So like that, you have to expand and you have to apply various Boolean algebraic theorems and all. You can simplify this. So you can also simplify this one in the same way. Just expand and apply the Boolean algebraic theorems and laws and then simplify it. For each of the following expression, construct corresponding logic circuit using AND or invert logic. So what we need to do, we need to simply draw the avoid logic circuit, or else we can also say that this problem is asked to implement the Boolean functions using logic gates. Okay, so what is the first function given? The first function given is AB, that is y is equals to AB into C plus D. So now I want to implement this one using logic gates. First I am taking AND gate, to which I am giving the two inputs AB, and then I am taking an OR gate, so to which I am giving the two inputs as CD. So the output of this one is C plus D, whereas the output of this one is. So now I can use an AND gate. So finally I want to multiply this. So now I can get the y is equals to AB into C plus D. So like that you can implement. Even this was also implemented where the complement can be implemented using inverter. Now implement that Boolean function y is equals to AB complement plus A bar B complement. So this is nothing but an XOR gate. How to implement XOR gate using NOR gate. So the similar fashion which we have done for the sixth question, we have to do for this question also. But here the thing is we want to implement this using NOR gate. So what we can do here, so the procedure is different. What is that? First place the bubbles at the outputs of the OR gates and at the input side of the AND gates, and the remaining all the steps are same. And finally we need to replace all the bubbled AND gates with NOR gates, because bubbled AND gates are equivalent to the NAND gates. So that is how you can get the NOR implementation of A bar B plus AB bar. Okay. So that these are all the questions that are analytical questions given in the question bank. So you can go through them. And now let us see the long answer questions. So how to answer the long answer questions. So the first question in this, explain error occurred in data transmission can be detected using parity bit. Explain how error occurred in data transmission can be detected using parity bits. So we need to, we know that we have error detection and correction codes. So the error detection and correction codes are parity and Hamming code. So parity code is used for only detecting the error, whereas it cannot be used for correcting the error. So here now, first of all, how to answer this? First, what we need to write, what is a parity bit, and what is the significance of parity bit. So a parity bit is an extra bit added to a string of data bits in order to detect any error that might have crept into it while it was being stored or processed and moved from one place to another place in digital systems. So we need to write down their parity and how many types of parity we have, we need to write and take an example like this. So how can we, this parity bit is added at the transmission side. So by following either even parity or odd parity, and at the receiver side, the receiver will check whether the received message is having or else is following the parity followed at the transmission side or not. That means if we have considered even parity, then the receiver side, the receiver will check whether the received code is having even number of ones or not. If it is not having even number of ones, then he can conclude that this message is having some error. So like that he could detect the error. So how can he detect the error? If the parity is not, if the parity at the receiver side is not matching with the parity at transmission side, then he can conclude that there is an error. But he could not identify where the error is existing. So that is a major limitation of parity bit. So these are all the things you need to write. First, you have to define what is parity bit and what are the various types of parity bits. Define even parity and odd parity and how it is used in transmission. So at the transmission side, the transmitter will add an extra bit and at the such that either even parity or odd parity is satisfied. And at the receiver side, the receiver will check whether the parity is maintained same as the transmission side parity or not. If the parity is deviated, then he can conclude that there is an error. So this way you have to write down or else you have to present the answer for this question. And here is an example. So we have taken various datas. and the parity bits which are to be added when the even parity is considered and odd parity is considered. So this way you can present so that you can get the full marks. Now define weighted codes and non-weighted codes with example. So first of all, give the significance of codes, binary codes. Why we are going for the binary codes? Why we are going for the binary codes? In order to reduce the storage and in order to make the transmission easy, we are going for the binary codes. Binary codes, nothing but grouping of binary data, is called as binary codes. So the binary codes are of two types again. So weighted codes and non-weighted codes. So define weighted codes. So what do you mean by weighted codes? So weighted codes are the binary codes in which each bit is having its own positional weight. That means these are the codes which obey the positional weighing principle. Okay, and give the examples of weighted codes. So like 8421 code or else BCD code. Not only 8421, even 2421 code is also called as a weighted code. So give some examples and explain them with some truth table. So draw the truth table for 8421 code and also 2421 code. So this is how we can write the weighted code. And now non-weighted code. Non-weighted code means these are the binary codes which does not obey the positional weighing principle. That means each digit in this code will not have positional weight. Okay, so the codes are written based on some logic. And the examples of non-weighted codes are XS3 code and gray code. So just give the XS3 code and 4-bit XS3 code and the gray code truth table so that it will be well and good. This answer will be sufficient for this one. Next, explain what do you mean by error detection and correcting codes with example. So we need to write down what do you mean by error detection and correcting codes. So these are the codes, binary codes used to identify the error, presence of error and correct the error while transmitting the data from one place to the other place. So we have two types of error detecting and correcting codes. What are that? Parity bit and Hamming code. Okay, parity code or else Hamming code. So define parity code and give some example. Okay, define parity code. So what we need to define? Define parity bit and what are the types of parity bits, how the parity bits are used as error detecting codes we need to explain by taking an example. So similar fashion we just discussed about parity code. And similarly Hamming code. Hamming code is said to be error detection and correction code. So you just write down the limitations of parity bit. What are the limitations of parity bit? The limitations are this can be used only for detecting single bit error and it cannot be able to locate the error. That means it cannot be able to find the position of error, the parity bit. So that is why we are going for the Hamming code. So write down the steps of Hamming code algorithm and take one example like any 4-bit message you take and derive the Hamming code for this one. So that is how you can answer this. So write down the Hamming code, that limitations of parity bit and the uses of Hamming code. That means advantages of Hamming code over parity bit. What are the advantages? Not only it can detect only a single bit error. It is also a limitation for this. If more than 1 bit errors are happening in that, this Hamming code cannot be able to detect multiple bit errors. And even it can correct the single bit errors only. So this you have to write. Okay. So this is the way you can answer this question. Take some example and explain how the parity bit is used to detect the error and how to generate Hamming code, how the Hamming code is used to detect the error. Okay. Now explain gray to binary and binary to gray code conversions with example. Okay, so here gray to binary code. So we already know that if we have a gray code, the binary code can be obtained simply. For example, this is gray code G3, G2, G1, G0, and this one is binary code B3, B2, B1, B0. So G3 and that is MSB and LSB, or MSB of gray code and MSB of binary are same, whereas the gray code can be converted into binary. How can we convert this? The MSB XOR with the next bit of gray code will give you this one. Similarly, the MSB, the XOR of these two will give you this, whereas the XOR of these two will give you this. So that means I can write on that B3 is equals to G3 and B2 is equals to B3 XOR G2. Similarly, B1 is equals to B2 XOR G1 and B0 is equals to B1 XOR G0, or else we can also write on B3. In place of B3 I can write on G3 XOR G2, and in place of B2 I can write this one, G3 XOR G2 XOR G1. Similarly, B0 I can write it as G3 XOR G2 XOR G1 XOR G0, like that. So take one example. Take a gray code 1100. This is a gray code. And now write down the binary equivalent for this one. How can I write the binary equivalent? 1. This 1 XOR 1 is 0. 0 XOR 0 is 0. And 0 XOR 0 is 0. So this is the 4-bit binary equivalent for the gray code. Similarly, how to convert a binary number into gray code? So we have a binary number, 4-bit binary number. Now I want to convert this into its equivalent gray code, right? How to? So again MSB or same. The XOR of these will be G2. The XOR of these will be G1. The XOR of these will be G0. So that means again G3 is equals to B3, whereas G2 is equals to B3 XOR B2, and G1 is equals to B2 XOR B1, and G0 is equals to B1 XOR B0. Similarly, take one more. So for example, let us take 100 is my binary number. Now if I get the gray code for this, I should get this one. Whether I am getting this or not, I'll check. So the MSB is same, whereas this 1 XOR 0 is 1, 0 XOR 0, 0, 0 XOR 0, 0. So this is equal. So that is how you can get the binary code or else gray code for the given binary number. Okay, so like that you can convert any gray code into binary code, and also any binary code into gray code by using XOR operation. So this is how first you explain how to convert a binary to gray and gray to binary. Take one example, get its binary code and gray code, its equivalent gray code. So explain the conversion of AND or NOT logic into NAND or NOR logic with examples. So what does it mean? It is just nothing but multi-level NAND NOR implementation. Multi-level NAND or NOR implementation. That means for this question you need to answer this one. Multi-level NAND or NOR realization. So that means we need to first draw the, mention the steps of converting any AND or NOT logic into NAND or NOR logic. So these are the steps here. Draw the AND or invert logic for the given Boolean function, and then convert the, if you want to convert AY into NAND logic, so just now we had discussed, place the bubbles at the output side of AND gates and at the inputs of all the OR gates. And if NOR logic is chosen, what should we do? Opposite. We should place the bubbles at the outputs of OR gates and inputs at the, place the bubbles at the inputs of AND gates. And then finally, place an inverter on each line which has received a bubble and eliminate double inversion. And in case of NAND logic, replace all the bubbled OR gates with NAND. And in case of NOR logic, replace all the bubbled AND gates with NOR gates, right? So this is the procedure you have to mention, and take any one simple function like y is equals to a bar b plus a b bar and implement this using both NAND and NOR gates so that you can get the full marks. With example, if you can implement, or else with you can discuss the procedure so you can get the full marks. Difference between BCD code and 2421 code and XS3 code. So what should we do? We know that BCD code, okay, BCD code is nothing but binary coded decimal. Binary coded decimal. Okay, so just explain what is binary code decimal. And 2421, what is 2421 code and XS3 code. And then draw the truth table. Okay, draw the truth table So BCD code and 2421 code and then XS3 code. XS3 code. Okay. So write down the decimal digit 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So BCD code for this one 0, 0, 0, 0, 0, 0, 1. Next 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, next 1, 0, 0, 1. Like this you have to write. And then 2421 code. 2421 code means what is the maximum value that we can represent using 2421? What is the maximum addition of positional weights? 2 plus 4, 6, 8, 9. 9 up to 9 we can represent. So write down it's for the decimal number 0, what is the 2421 code 0, 0, 0. Like that you write down the 2421 code. XS3 code. How can we get the XS3 code? By adding 3 to the number, we can get the XS3 code. So that means for 0, the XS3 code will be 0, 0, 1, 1. 0 plus 3 is 3, right? 3 in binary can be represented as 0, 0, 1. 1 plus 3 is 4. So that is represented as 0, 1, 0, 0. 0, 1, 0, 1. 0, 1, 1, 0. 0, 1, 1, 1, 0, 0. 1, 0, 1. 1, 1, 0. Oh, sorry. 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0. So these are the XS3 codes. Similarly, we can write down the code for this one. So 1 can be represented as, next 2 can be, next 3 can be, and 4 can be, 5, 0, 1, 0, 1, 6, 0, 1, 1, 0, next 7, 0, 1, 1, 1, next 8, 1, 1, 1, 0. Next 9 is 1, 1, 1. So these are the differences between XS3 BCD code, 2421 code, XS3 code. So these are all 4-bit codes only, but only the thing is in each and every code we are following some of the technique here. So this is like this you can differentiate between the BCD code, 2421 code, XS3 code. And write down the first 10 decimal digits in base 3 and base 16. Base 3. Base 3 means, so here we have to write down the decimal numbers. So these are the decimal numbers. What are the decimal numbers? First 10, that is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So these are the first 10 decimal digits. Now in base 3, how can we represent? And then in base 16. Base 16. So base 16, how can we represent this? So here 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Up to 9 we can represent like this. And whereas in base 3, what is the maximum symbols we can have? 0, 1, 2. Only these symbols can be used. So 0 can be represented as 0, 1, 2. Whereas 3, how can I convert 3 into base 3? So 3 is a decimal number. I want to convert it into base 3. So then I have to divide by 3. 3 ones are 3 with a 0. So that means 1, 0. Whereas 4 can be represented as 1, 1. 5 can be 1, 2. And 6. How can I represent 6 in decimal number 6 in base 3? So we need to divide the 6 by 3. 3 2s are 6 and it is 0. So 2, 0, 2, 1, 2, 2. Okay, so like that you can represent. So for example, if we have 10, 11, 12, 13, 14. It is not asked, but for your understanding, I am telling you. 10 can be represented as 3, 0, 3, 1, 3, 2. Right? Next. Just a second. Okay, sorry. This 9 can be represented as 3, 0. Whereas 10 can be represented as 3, 1. And this is 3, 2. This 12 can be 4, 0, 4, 1, 4, 2. And 15 can be 5, 0. Like this. Whereas in hexadecimal, 10 to 15 can be represented as A, B, C, D, E, F. Like that you can present. So this is the representation of decimal digits in base 3 as well as base 16. The thing you have to remember, in base 3 we have only 3 symbols. Those are from 0, 1, 2. Now, a device that transmits binary data using even parity. The message is 1011001. Identify the receiver receives the correct code or not. So this we can do by using Hamming algorithm. Hamming code algorithm. So here the message transmitted is given and we need to find out whether there is an error or not. So again we need to construct the same table. So that is bit position, next bit designation, and then binary position. And then bit value. Right? This is a table we need to construct for this. So what is the number of bits given here? 1, 2, 3, 4, 5, 6, 7. 7. So 7, 6, 5, 4, 3, 2, 1. Right? So now again we need to identify the, so as we all know that according to the Hamming algorithm, in all the powers of 2 positions we have parity bits. So this is P1, P2, P3, and these are all the message bits, M4, M3, M4, M3, M2, M1. Write on the binary positions 1, 1, 1, 1, 1, 0, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 0. And I write down the bit position values here. 1, 0, 1, 1, 0, 0, 1. Now generate the syndrome C1, C2, C3. So how many parity bits here? We have 3 parity bits. So for that we need to generate 3 check bits. So check bit 1 can be represented by looking at the positions 1, 3, 5, 7. 1, 3, 5, 7. Right? So now what is the value of 1? 1 is 1, 3 is 0, and 5 is 1, and 7 is 1. So what is the parity used here? Even parity. What is the number of ones present in this? It is odd, that is 3. So that is why check bit is considered to be, it is 1. It is considered to be 1. Similarly, C2 can be calculated by 2, 3, 5, 7. 2, 3, 6, 7. 2, 3, 6, 7. Because second bit position. 2 is having 0, 3 is having 0. Okay. 2 is having 0, 3 is also having 0, 6 is 0, and 7 is 1. Again it is odd. So C2 is also considered to be 1. C2 is also considered to be 1. Next C3, that is 4, 5, 6, 7. 4, 5, 6, 7. 1, 1, 0, 1. So again it is having odd number of ones. So C3 is also 1. So that is 7th bit position. So now the syndrome can be written as syndrome which is able to identify the location of error bit position C3, C2, C1, which is 111, whose decimal equivalent is 7. So that means this position is having error. Like that you can detect the error. Okay. Now same way, solve the given 8-bit data word, generate 12-bit composite word for the Hamming code that corrects and detects single bit error. So using the Hamming code algorithm, you just generate a 12-bit. So he already given. So this is the Hamming code length is 12, whereas the message bit is given as 8-bit data. So that means 4 bits are to be added, which are the extra bits, which are the parity bits. So just add it and generate the Hamming code using the algorithm. Now convert the given Boolean function into standard POS or else canonical form. So how to convert? First identify the missing variables in each and every term. So that is A plus B. C is missing. So add a term. So as it is POS, add a term formed by adding the missing variable and its complement. So A complement plus B plus C, and here B is missing, A plus C plus B into B complement. So now expand this one using distributive law. So I can write it as A plus B plus C into A plus B plus C complement, and even I can write this one as A plus B plus C into A complement plus B plus C, and this I can write it as A plus B plus C into A plus B complement plus C, right? So in this, these terms are repeated. So I could consider only once A plus B plus C, and the remaining terms are A plus B plus C complement, and next A complement plus B plus C, and next A A plus B complement plus C, right? So this is the canonical form where each and every term includes all the three variables of the given Boolean function. Even you can write it as max term. What is the max term here? This is 0 and this one is 0, 0, 1. This is M1 into this one is M4 into this one is M2. Okay, this is M2. So like that, I can write this one as pi m of 0, comma 1, comma 2, comma 4. So this is the canonical form or standard form. Now give the Boolean expressions, symbols and truth tables for all the following logic gates: AND, NOR, XOR, OR, XNOR. So give the symbols, first AND gate symbol and its truth table. This is the first one. And the second one is NOR gate symbol. NOR gate symbol, you know, OR followed by the bubble. Next, the third one is XOR. XOR, you know. So whereas the truth table and that you have to write. OR gate, you know the OR gate symbol. So this is the OR gate. And fifth one is XNOR. Okay, XNOR. So the symbol of this one is XOR with a bubble. So whereas, for example, A, B here, this is C is equals to A dot B. Whereas C is equals to A plus B whole bar. Whereas C is equals to A XOR B. Okay, and this one C is equals to A plus B, and this one C is equals to A XNOR B. Okay, so like that, and draw the truth tables also. As you all know the truth table, you just draw the truth tables. Implement all the logic gates using NAND and NOR gates. So this I have discussed already. So as you all know that NAND and NOR gates are universal logic gates. Why these are called as universal logic gates? Because any other logic can be implemented using these two logic gates. So that is why we are calling this as universal logic gates. So just draw the logic circuits of all the logic gates using NAND and NOR. So that will be the implementation. Now simplify the Boolean function, that is AB plus AB bar into A complement C complement whole complement using Boolean algebra. So expand that and simplify it. Okay, so I hope you can do this. AB plus AA complement B, just a second. So A B complement into this one. How can I write this one? Complement A plus C. Okay, so now just expand this one. So AB plus AB complement into A plus AB complement into C, right? So now I can write it as AB plus AB complement plus AB complement C. So now I can write, again do this one as AB plus AB complement I am taking as common. AB complement I am taking as common here. So I can get 1 plus C. So AB plus, so AB complement. So now I am taking A as common, B plus B complement. So what I can get? A into 1. So it is A. Okay. So because B plus B complement is 1 and similarly 1 plus C is 1, right? So like that you can simplify this one and simplify the following 3 variable Boolean function using Boolean algebra. First you have to write down the Boolean function. What is that? Summation M of, this is summation actually, summation M of 357. Summation M of 357. So actually it is given capital M 357. That means it is a product of sums expression. So how can I write this? So let us consider it is a function of A, B, C. So M3 nothing but 0, 1, 1, 1, 0, 1, 1, 1, 1. So what is the max term for this one? So that is A plus B complement plus C complement, and this one A complement plus B plus C complement into A complement plus B complement plus C complement. So you take this, apply all the Boolean algebraic theorems and laws, simplify it. State and prove Boolean theorems and properties. So here you need to write down all the theorems and properties of Boolean algebra along with the proof, so that you can get the full marks here. First, list all the properties along with the proofs, okay, which I have discussed in Boolean algebra, the theory, concept, and in one lecture. So you can go through them. So you have to remember all the theorems and properties and their proof. If it is not able to prove mathematically, you just draw the truth table and prove whether LHS is equals to RHS or not. If LHS is equals to RHS, then also the proof is done. So like that you can prove. So these kind of questions may be asked from module 3, that is based on number systems and Boolean algebra. So even logic gates. So I hope now you can answer any type of question that is asked on the module 3, that is asked in from module 3. So that's all for this lecture. Thank you everyone.
Like, share and subscribe. Hit the bell icon for more updates.